Starting within few seconds. It started.
Okay, all right, thank you. So we'll get started. Hi, everyone. Welcome to our day 2. This is our 6th session of the GIAN workshop. Thank you for participating and welcome back. I hope you all had a useful and interesting first day. I definitely think there is a lot of information that we shared with you. I know Professor Aligaonkar also had a session, the last session of the day, where you were introduced to some of the WLCA practices or sustainability practices in India. So today in this session, I'm going to move forward and introduce to you in more detail the RICS Whole Life Carbon Assessment Standard, the second edition of the standard. So before I do that, I'm going to just sort of give you a recap from our day 1. I think we started with painting a big picture, reconfirming the importance of sustainability in the built and natural environment. We talked about the environmental, social, and economic aspects of sustainability. We, in the first session, tried to make connections with sustainable development goals. And then in order to make a more practical, detailed project and asset-specific connection, we also described the donut economics framework, which helps you see the interconnectedness between social and environmental aspects of sustainability. We also then briefly talked about the nationally determined contributions as a tool to start at the sector level. Obviously, every country determines NDCs, and for that, every country, then you make the connection between the sector level mandates down to perhaps an ecosystem of companies, their projects and assets, so that you can do a top-down approach and make connections with the carbon emissions coming out of individual projects and assets. Then in the next section, we sort of introduced broad brush what LCA means and how LCA plays an important, crucial role in our decarbonization journey. We looked at LCA at the product, service, and material level. We also looked at LCA at the system component and assembly level. And then finally, we talked about whole building infrastructure and asset level LCA also. We briefly described the step-by-step process for LCAs, and I gave you global context of how LCAs are conducted globally. And Professor Aligaonkar in the last session, I saw portions of his recording on YouTube, talked about the various IGBC and other frameworks that are used in the Indian context to talk about sustainability broadly and decarbonization in a bit more detailed fashion. So from that, I think what I would like to do is perhaps open the floor for a few minutes, see if anyone has any questions, suggestions from yesterday. I think we did address most of the questions. So thank you, Abhishek, for your comment on the book, handbook that I've co-authored. But looking back yesterday and perhaps considering the agenda for today, I'm going to give you a chance and to see if you have any questions or comments or suggestions. You can either turn on your mic. If you're in the room, you can speak up there. Otherwise, you can type it using Slido also. So in Slido, you can either scan the QR code or you can go to slido.com, punch in that number 1449487 and type in your question there. Any question from the room? Yes, I see a hand go up.
Good morning, Professor Sawhney. This is Abhishek Rapsang.
Hi, Abhishek.
Yeah, Professor Sawhney, first of all, congratulations to our new edition of Conception 4.0.
Thank you.
Yeah, my question, Professor Sawhney, is related to the thing that you mentioned that if we are calculating it for the first initial step of our construction, like your transportation, your acquisition of materials, my question lies there if garbage data is being fed in because manufacturers don't have the data for Indian constructions right now.
Yes.
So in that case, if any garbage data is being fed into the model, how much significantly it impacts the analysis result, and what is the proportion size that it deviates the actual results from the true? That's my question.
That's an excellent question. I think for us, globally, data is a big challenge. Emissions and carbon factors are not easily available, especially in developing or emerging markets. We are going to talk a little bit about some thumb rules. Again, those thumb rules are based on historical data. That historical data is again not very much available in different parts of the world. So it is a challenge. I brought today some examples on how we can address that. So Abhishek, maybe when I go to that section of today's presentation, maybe we can revisit your very important and timely question. So we could have perhaps a little discussion at that time also. So I did bring an example of ready-mix concrete, an Indian carbon factor information for ready-mix concrete. I'm sure you guys would have seen other similar data also. So we'll walk through some of the data and examples today, and hopefully that will clarify some of the information.
Sure, Professor. Thank you.
Okay. I don't think we have any other questions. So that means we can move forward. Maybe I'll pause another 30 seconds to see somebody online. Quite a few have you joined online. So if there are any questions, please feel free to either raise your hand, put it in the chat box, or just simply turn on your mic and speak. Okay, so assuming we can move forward, I'm going to just give you, for the first session, I'm going to talk about WLCA and also Scope 1, Scope 2, and Scope 3 emissions. We'll then talk about a little deep dive into the RICS methodology for calculating carbon emissions. And then we'll start moving into emission calculations. I'm hoping to cover module A today, and then hopefully we can do B, C, and D tomorrow. So that's the overall plan for today. Let's jump right into the introduction of WLCA and Scope 1, 2. I guess 3 is missing, but Scope 1, 2, and 3 emissions. So we closed yesterday by looking at the broad view of life cycle assessments and its adoption in the construction sector. Remember, we made certain changes. We clearly saw that LCAs can be applied to an individual product or material like cement, ready-mix concrete. It can be applied to an assembly like perhaps mechanical equipment in a building. And it can also be applied at the asset or the project level. WLCAs adopted from LCA into the built environment sector focus right now primarily on GWP, the global warming potential of the emissions. And we measure all emissions right now in carbon dioxide equivalent values only. So the benefits of using WLCA for us is that we can improve the way the greenhouse gas emissions, GHG emissions, are reported. Many companies and organizations are required to now report GHG emissions. So these GHG emissions need to be calculated in two ways. Right now, large companies, when reporting emissions for their company level, organizational level reporting, for example, in the US, SEC, the Securities and Exchange Commission, requires as you provide your financial reporting, you also have to do sustainability reporting. So many of these large companies right now utilize a sort of a money or spend based analysis. So they do a very high level assumption. They assume that if we spend $1 million in certain part of our operations, the emissions from that activity based on the dollar value of spend is utilized to do GHG reporting. So they do not go down to the level of going into individual asset that they own. Let's say you're a large developer with many buildings, some new builds and some existing buildings. And if you're required by law to report on sustainability and emissions, what they do is sometimes they will utilize a spend-based reporting. So connect emissions to the dollars amount of money that is spent, use that to provide the emissions. But if you use WLCAs, you can perform whole life carbon assessment calculations, find emissions from each of your project, from each of your asset, combine your entire portfolio, and then enhance your GHG reporting. Through WLCAs, you can also do meaningful benchmarking. So emissions is something that you have to demonstrate. Some parts of a company's operation can remain confidential. So for example, cost generally is not publicly shared. But in the case of emissions, you have to demonstrate, you have to make your emissions visible, meaning you have to transparently share how much emissions are coming from your building. So through WLCA, we can make the emission calculations benchmarked against each other so that you can demonstrate that your buildings, your assets, your infrastructure assets are performing better. So it also can help you establish early design baselines. So if you're performing WLCAs and you're storing your assessments in a database, that database can eventually help you give some benchmarks which you can use for early design baselines. Like we do in costing, somebody comes up and says that they want to do a school building. They don't have much detail. They maybe know the location. They maybe know the target number of students that they want to have in the school. You can use benchmarks and baselines to do an early cost estimate for that school building. So very similarly, if you start using WLCA and you start reporting those WLCAs, you can build your baselines and benchmarks. So the next new project that you do, you can utilize those benchmarks, and WLCA helps in a big way. WLCAs can be used for supporting carbon targets and policies. They encourage long-term thinking and long-term and resilient thinking. So it introduced that idea of whole life approach to all our decision making. It supports circular economy principles. I think one of the sessions, Professor Aligaonkar is going to talk about circularity. So how circular construction is becoming an imperative. We also then help enable better tools and net zero alignment if we use WLCAs. So as I previously mentioned, so if you start using WLCA, you can move away from spend-based calculations. You can actually find your emissions by your asset, by your project, in your portfolio, and then you can report scope 1, scope 2, and scope 3 emissions. I will share with you briefly after this what is meant by scope 1, scope 2, and scope 3 emissions. Because you're performing WLCA, you can clearly specify the roles and responsibilities. When we talk about scope 1, scope 2, scope 3, you will see what exactly I mean by this. This WLC also supports alignment with global carbon reporting frameworks like GRESB, CREM, or PCAP. These are global reporting frameworks for your portfolio. It provides detailed and structured emission data for ESG reporting and climate-related disclosures also. So WLCA has definitely this benefit. With WLCA, you can standardize your carbon assessment. So let's say you adopt the RICS WLCA methodology for doing all your project assessments, then it's standardized. And since it's standardized, you can start comparing between assets which are better performing, environmentally better performing assets versus which ones are not. And then you can make decisions accordingly. It enables a consistent whole life carbon performance tracking for design through commissioning. It supports and builds robust national and regional benchmarking databases. We are building such a database in the UK called the Built Environment Carbon Database. So people are reporting their assessments, which are consistent. Those reports are then used to generate benchmarks. So as this database grows, you can see that initially at the asset level, we can give you benchmarks of typical embodied carbon. Somebody asked that question also. These benchmarks, targets, limits cannot be just picked from thin air. They need to be built on historical information and sometimes top-down sectoral calculations also. So once you have your WLCA database, for example, in place, you can utilize it to establish design baselines. So early in the process, you can guide your clients, you can guide the decision makers in seeing the kind of carbon emissions without having too much data, detailed design available for your project. So it helps promote iterative carbon assessment, then informs each project phase from concept to delivery and up to end of life. Supporting carbon targets and policies. So if you're using WLCA, it enables reliable carbon target setting across upfront, embodied, and operational carbon categories. So regulatory bodies, planning folks, and others, voluntary sustainability schemes can be used to then set those targets and implement those policies. So if you are in Vancouver, for example, they have set their own targets. If you're in Toronto, there are targets set. Many other places in Europe also, there are targets being set. If you're an office building, you're given a limit or a target for emissions from your projects and assets. Without doing WLCA, it is really not possible to undertake these kinds of targets and policies and limits. Through WLCA, as we've been discussing, it helps push the industry towards long-term resilient whole life thinking. It helps you assess future maintenance, repair, and replacement needs and their carbon performance, because no longer you are making material selections and decisions by just looking at the construction phase. If you are doing a whole life carbon assessment, you're forced to think when the roof will be replaced, when the mechanical systems will be replaced, when do you need to repair or maintain maybe the doors and exterior doors and windows. So all those things have both cost and carbon associated with them. So if you are to repair or replace the roof of a school building in 25 years, then you know that there will be a cost associated with it and there will be emissions associated with that intervention. So with the whole life thinking and use of the whole life carbon assessment methodology, you're able to see these things and make decisions accordingly. So it helps therefore push use of long lasting, low maintenance materials that reduce the whole life impact, rather than just selecting materials and components that are useful in the construction stage itself. So you're not making short-term decisions. It supports, if you're doing WLCA, remember it has those 4 modules. You have module A, which is product and construction. You have module B, which is the use stage, and then module C, which is the end of life stage. So if you have end of life stage, you are basically able to then make decisions about the recycling, recovery, reuse, and its proper calculations within the whole life carbon assessment. So this promotes circularity in the building sector. So those are the benefits of using whole life carbon assessment. As I mentioned, through the use of WLCA, you can improve and enhance your emissions reporting across the GHG protocol's 3 scopes. So the greenhouse gas GHG protocol, you can go to their website and review all this, categorizes emissions into 3 scopes or categories. First is scope 1, which is the direct emissions from owned or controlled sources. So assume you are the reporting entity. So let's say VNIT is submitting a GHG protocol report on emissions. Any emissions that comes directly from their owned or controlled sources is called scope 1. Scope 2 emissions are indirect emissions from purchased energy, purchased water for your assets. Scope 3 is all other indirect emissions from the value chain. And this probably scope 3 is the most important, but the most difficult and complex to calculate, but it applies the most to the construction sector. So these scopes help organizations identify, manage, and reduce emissions across their operations and supply chain. So if you're the reporting entity, it helps you do that. Most organizations and most requirements currently ask you to report scope 1 and scope 2. They realize that reporting scope 3 is difficult. So scope 3 emissions are generally not calculated and reported, but it should change. It will change if you're doing WLCAs, and I'll share with you perhaps tomorrow or the day after how, after doing a WLCA for your building, you can then categorize scope 1, scope 2, scope 3 emissions. So scope 1 emissions are also called direct emissions. These include emissions from sources directly controlled by the reporting entity. So all fuel consumption for company-owned machinery and vehicles is going to be scope 1. Any on-site fuel usage for generators, boilers, heating, etc., are also scope 1 emissions. So anything, you are the reporting organization, anything in your direct control, emissions coming from that are considered scope 1. Fugitive emissions from refrigerants used in temporary site cooling systems, for example, would be scope 1 direct emissions also. Scope 2 indirect emissions are essentially emissions that come from purchased electricity, steam, heating, or cooling for your assets. So your company maybe buys energy from an external provider, the emissions related to that purchase are categorized as scope 2 indirect emissions. So you are a construction company, for example, then all the electricity used in site offices and whatever else you have on site is contributed to scope 2. So all emissions coming from temporary construction equipment are also scope 2 emissions. Scope 3 are all other indirect emissions. So scope 3 is difficult to calculate because it's all other indirect emissions occurring in the value chain. So examples in construction would be embodied carbon in purchased materials like concrete, steel, timber, transportation of materials and workers to the site, waste disposal from construction sites, any business travel, any emissions from the use and maintenance of built assets related to your value chain all come under scope 3. So if you are looking at a construction project, a significant portion of the emissions that you calculate using WLCA would be categorized as scope 3 emissions. So this is from the GHG protocols website. So greenhouse gas emissions protocols technical guidance sort of shows you how this matters, or how is it the scope 1, scope 2, 3 all fit together. These are your emissions, GHG emissions that we talked about yesterday, the Kyoto gases or the Paris Protocol gases. So your carbon dioxide, methane, and all those gases are here. Scope 1, you are the reporting agency or you are the reporting company, you are a construction company, then perhaps all emissions that are in your direct control, all your offices, all your vehicles, all emissions coming from those directly go into scope 1, which is the direct emission. Scope 2 emissions are all the emissions that come from purchased goods and services, including purchased electricity, steam, heating, and cooling. So that goes into scope 2. Now, scope 3 can come from upstream activities and downstream activities. So it can come from materials that you buy, equipment that you buy, all of that upstream for your company's use, for your projects, all of that goes into scope 3, indirect from upstream activities. From downstream activities in your chain, let's say you're a manufacturer of doors and windows for the construction sector. So when you ship out these completed products, all emissions coming from transportation, distribution, all other aspects in the value chain are also allocated to scope 3, indirect emissions, as they're called, which come from your value chain. So this is sort of the connection we have with scope 1, scope 2, scope 3. Primarily, there are two main things that you need to understand. As a company or as an organization, in many jurisdictions, you are required to report scope 1, scope 2, scope 3 emissions at the company level. If you are in the real estate infrastructure sector, then you need to start connecting emissions coming from your projects and assets to these scope 1, scope 2, scope 3 emissions. Right now, scope 1, scope 2 is primarily reported. Scope 3 is not mandated or fully reported. Currently, most companies use what's called spend-based reporting. So in all my operations, I spend $100 million. The carbon factor of that spend is found. You multiply the two and you report your emissions, especially scope 1, scope 2. But that generally is an inaccurate calculation. So our hope is that with the use of whole life carbon assessment, you will be able to calculate emissions for your module A, module B, module C, module D. And then a map can be provided where you can take these emissions from various modules and connect them to scope 1, scope 2, and scope 3. So if you had 100 buildings, if you combined all of them using this kind of a mapping, your ESG reporting, your scope 1, scope 2, scope 3, GHG reporting will become much more improved and enhanced. Okay, so that sort of concludes our first section, which was primarily focused on the benefits of whole life carbon assessment and its linkage to scope 1, scope 2, scope 3 emissions. I'm going to again have a brief pause and see if anyone has any questions from the room or from virtual or folks that were online. Any questions? Okay, it looks like we are all set. So let's move to the second portion, the more important portion of our session today, which is now moving into the whole life carbon assessment for the built environment professional standard that the RICS produces. So I work for the RICS, as you saw in my introduction. We actually produced, we meaning RICS, actually produced for its members. RICS is a global professional body with about 140,000 members. We produce standards and best practice guidance for our members. The first guidance we produced for embodied carbon was in 2012. Okay, so this is something that we've been working on for a long time with the help of our members. The first edition of this methodology or professional standard whole life carbon assessment was produced in 2017. Then 6 years later, in 2023, we have released the second edition of this professional standard. This is a free resource available to you, to our members and other stakeholders. So what is it really do? It is a standard that sets out an RICS approved technical calculation methodology for measuring carbon impacts from buildings and infrastructure throughout their life cycle. And that's where the whole life piece comes in. All RICS members are regulated and they must use the mandatory requirements of this assessment, the assessment methodology within the standard. So if you are an RICS member and you're doing a WLCA or an assessment for your building, you are by regulation required to comply with the mandatory requirements of our standard. So as I mentioned, 2017, we released the first edition of the standard. At that time, it was applicable only in the UK. It was regulated and used in the UK. But nevertheless, folks globally have been using our standard for a long time. Then about 3 years ago, a decision was made to release the second edition. You will notice the second edition has gone global. So this is a globally applicable standard from the first edition, which was UK based, to now a globally applicable standard. It now includes methodology to calculate emissions from all types of projects: infrastructure projects, housing or projects, small residential projects, to retrofits. Okay, it is connected to another standard called ICMS, which we are going to discuss today, so that the standard can not only calculate carbon emissions, but it can also connect to cost, because most decisions about reducing carbon emissions should be made in a cost-effective fashion. So in order to do that, we need to connect cost and carbon together, and an assessor can produce not only or calculate not only the carbon emissions, but is also able to calculate the cost associated with that design. Okay, so the document that we have now released in 2023 is about 220 pages. It has lots of explanation and diagrams. So unlike, let's say, an EN standard, which is very limited in explaining how things are done, it just lays out the standard. Our standard tells you the mandatory requirements, but also does a lot of explanation module by module. The audience for our standard is all these major stakeholders in our industry. So a developer can use our standard to basically do assessments for all their existing and new builds. So existing portfolio or new builds. Cost consultants, which RICS also calls them quantity surveyors, can use our standard to do cost and carbon calculations. Building surveyors, designers, engineers, consultants, all those folks are also an audience for our standard. ESG consultants, construction companies, policymakers, local authorities, lenders, and investors can all use the standard. And you will see that the standard has been adopted by, for example, the Climate Bond Initiative and so on. So this standard has linkages to finance, lenders, and investors also. So the WLCA standard, the second edition, as we saw the benefits of WLCA, now you can see it more clearly. You can use our standard, which is basically a technical methodology, to estimate the amount of carbon emitted throughout the life cycle of your constructed asset. It can be a building or it can be an infrastructure. Our standard gives you visibility to embodied carbon, operational carbon, user carbon, and also biogenic carbon, as I was mentioning yesterday. It helps you deliver against so we basically have we can deliver against both government and client demands for net zero buildings and infrastructure. Then we meet client demand by measuring and managing carbon emissions in a reliable and consistent manner. Our standard helps you take a long-term view of cost and carbon. So you're just not worried about CapEx or your construction cost. At least you can calculate and collect information over the asset's life cycle and then make better decisions, which basically then promotes sustainable and low carbon building and infrastructure investments in our industry. So the standard that we've produced essentially applies to those 5 life cycle stages of production and construction, operation, end of life, and beyond asset life, as we had discussed yesterday. So our standard, the WLCA standard, which is essentially, as I said, a methodology for calculating emissions, has these basic design principles that I'll explain in a little bit more detail. It is consistent, practical, comprehensive standard. It's integrated into existing workflows. So it's not like you're designing, you are engineering your building, and separately somewhere sitting over here, you're doing your carbon emission calculations. We have created an integrated workflow where it makes that connections. It's aligned with cost planning, and that's done through ICMS, which I will try to explain as well today. So the methodology is data-driven. It's integrated with building information modeling, or BIM. It considers both carbon costs and benefits, and is also linked to carbon management. So here are the key design principles. The WLCA standard that we have produced is consistent. So it is based on a methodology. It clearly tells you how to make assumptions and which data to use, at which life cycle stage, what data you should be using. So it's again a best practice guidance which is consistent. It's practical. So unlike ISO and EN standards, which are basically high-level principles and mandatory requirements, our standard also provides best practice. It also provides heuristics or rule of thumb to make assumptions, to make calculations when you have limited data. It's comprehensive. We cover all modules, all system boundaries, product and project life cycles. The standard can easily connect to the core workflows of design, construction, post-construction workflows, and can work very well with regional and national benchmarks. It's aligned to cost planning. So through the connection of this standard to this other standard called ICMS and to our own RICS standard called New Rules of Measurement or NRM, the assessments can be combined with cost planning also. It's data driven, so we guide you every stage, every calculation, what kind of data source would work best for that stage. It's integrated with BIM, so you can use digital workflows for your calculations also. Carbon costs and benefits, this is very crucial. Because you want to make your decisions to optimize overall carbon performance, you got to be able to do the trade-off between cost and benefits. What does that mean? It basically means through WLCA, let's assume you have an office building in which you have to make a decision between a highly efficient window versus which is slightly higher in cost versus a standard window which is lower in cost. Okay, with WLCA, you don't just need to look at the first cost. You can actually look at the life cycle cost and the life cycle emissions. So maybe one of your options is high on embodied carbon but low on operational carbon. So there is a trade-off. The other one is low on embodied carbon, but perhaps very high in operational carbon. So you can see the cost and benefits of their design choices, material choices, product choices also. Our standard integrates well with other standards such as PAS 2080. For those of you who are not familiar, this is a UK standard for carbon management. So it's like similar to project management or similar to cost management. This standard shows how to do carbon management also. So if you want to download our standard, you can scan the QR code and download the PDF of the standard. Alongside that, you have lots and lots of other resources available to you. So reporting templates in Excel spreadsheet format, supplementary tables for MEP, for energy are available. You can also download the buildings, the element categories across which you need to report emissions. So it will be a simple table that shows you substructure, structure, services, and so on. So that elemental breakdown of categories or elemental categories are also available. So lots and lots of resources are available for free, which you can download and use. So since its launch, about 30,000 downloads of our standard, which is a pretty big number. And then lots of other awards and finalists. So we have won the Engineering Matters Award in 2024. And we were also finalist in some other awards for this standard. So it's well recognized, quite heavily used standard that our members are required to use. So you want to know more about the standard, you can go to this website or that QR code that I had shared. Some examples of endorsements and supporters and users. Department of Transport UK, for example, Zero Waste Scotland, Transport for New South Wales in Australia. All these folks are public adopters and endorsers of the standard. So these are some of the endorsements we have received for the standard. So it's quite well recognized. Another example, the Transport for New South Wales in Australia has adopted the RICS second edition of the Whole Life Carbon Assessment second edition, ICMS third edition, and PAS 2080 as a suite of carbon decarbonization standard for their $72.3 billion pipeline of work. So all the three standards together are helping them improve their carbon performance of projects and assets. We recently signed an agreement with Expo City Dubai, and they'll be using the standard as well. I think this is sort of a repeat of what the Transport for New South Wales is doing, but it's essentially they have a digital engineering framework in which carbon is being added, and it's being added using these standards that I have listed here on the screen. So why do you need a consistent methodology for assessing carbon? Okay, so as we saw yesterday at a high level, you have various information modules across which you need to calculate your emissions. So broadly, module A, which is also called product and construction stage. You have module B, which is essentially your use stage, in which the project is completed and the asset is turned over to the operator and it's used. So module B. And then once the service life of this asset, or for some other reason, the asset has reached end of life stage, module C is used to calculate emissions resulting from end of life. And then you have beyond building life cycle. So there are various methodologies currently available. These methodologies, as you can see, have varying applications of the modules. Many modules are not currently incorporated into or used in these calculations. So if, for example, you're using the German standard, in that primarily coverage is for modules A1, A2, A3, and then very limited modules are covered. If you look at the RICS standard, we primarily cover most of these life cycle stages. This is a bit of a dated report produced by Ramboll, in which they have looked at our first edition. So even in our first edition, we had a lot of coverage, but now we have much broader and fuller coverage of all the modules. So in order to do consistent calculations, you cannot have this kind of a situation where you have so many methodologies out there, and these methodologies have varying level of availability of information modules and the calculations that go behind it. So that's number one issue that Ramboll pointed out. Similarly, there is quite a bit of disagreement and discrepancy between how this is for buildings, how we basically cover various building elements. So there are gaps, as you can see. So if you were doing, again, let's say the German standard, you may not have fully included all elements of the building in your assessment. So when you say whole life carbon assessment using the German standard, you may have different inclusions and exclusions, which again is not for producing consistent assessments and comprehensive assessments. There's another big debate actually right now going on. So this report, as you can see from Ramboll, is May 2023. Our standard second edition was released September 2023, so it doesn't fully address our second edition. Another finding from this Ramboll report was that, fine, we've done an excellent job calculating the total carbon emissions from our building. In order to report, we need to say tons of carbon dioxide equivalent per square meter of your building. But the way the denominator is calculated can vary. As you know, in India, we have super area, carpet area, and so on. So that definition itself is problematic and reduces the consistency that we are looking for in doing whole life carbon assessments, putting them into a benchmarking database and utilizing them for various purposes, not only showcasing the better performing assets, but also utilize that historical information to guide your new buildings in the early stages when not much project information is available. So it's another problem that must be addressed. The impact categories also vary. I've been saying to you from early on that most WLCAs including the one that RICS has, we primarily currently focus on GWP. Okay, we do not look at other environmental impacts. We don't look at these indicators. So, for examples, we do not include ozone depletion, acidification, and other environmental impacts. So that's another reason why we need to search for a globally consistent, comprehensive WLCA standard. So Ramboll did a study. They took a building in Sweden and in Denmark. They did the WLCA calculations. They only did certain portions. Using in Sweden, you can see that because we don't include all modules, the benchmark we got was 166 tons of carbon dioxide emitted compared to 423 for the same building in Denmark. Sorry, this should be 166 kilograms of carbon dioxide equivalent per square meter compared to Denmark, which shows 423. So how can you compare? How can you benchmark? How can you create baselines if the inclusions and exclusions from your assessments are not consistent? That's where our standard comes in, and we provide you with a very detailed whole life carbon assessment methodology. So I'm going to pause here again and see if anyone has any questions. Anyone online? Anyone in the classroom? Okay. Now let's sort of dive deep into the actual calculation. What I'm going to follow is the RICS WLCA methodology, but I think you will see other standards have very similar approach also. So the modular structure we are going to follow for computations is going to be that expanded RICS modular structure, which is adapted from 15978 primarily. So EN 15978, in which we broadly have our upfront embodied carbon. We have our in-use embodied carbon. We have end-of-life embodied carbon. We have upfront biogenic carbon. So we have upfront biogenic carbon reported under Module B, Module C, and Module D. Okay. Obviously, we have operational carbon B6, B7, which is water use, energy use, and then your user carbon, which is here. So let's begin with Module A and how we go about calculating emissions under each module for either a building or for an infrastructure project. Okay. Seems my screen just froze. So let's begin by going step by step, seeing the important aspects of calculating emissions for each module under Module A, the submodules A0 through A5. So we will include pre-construction, product, and construction stages. So first calculations are done for A0, which is also called pre-construction stage. Sometimes it's also called the acquisition stage. So our standard says under this calculation, A0, you need to cover all non-physical activities before construction starts. So you're on site, construction has not started. Any emissions that take place, maybe for surveying, maybe under soil investigation, maybe under any other site visits and so on, should be captured under A0. Obviously, the way I'm describing to you, for a simple building, A0 is negligible. So generally, as a rule of thumb, in WLCA standard, we do not report A0 pre-construction acquisition stage emissions for buildings. Imagine for a large infrastructure project, it's going to be significant, I shouldn't say substantial. So we need to calculate A0. The emissions that come from, as I said, site surveys, geotechnical or other kinds of investigations. Maybe you have soil investigation that requires heavy equipment that is diesel operated, emissions from that, all your site meetings, team meetings, all other aspects of emissions during the pre-construction acquisition stage, generally for infrastructure projects, are included in this A0 submodule of Module A. The next calculation is done for A1, which is a raw material supply. So A1 applies to both buildings and infrastructure. It is now you're calculating GHG emissions from the extraction, processing of raw materials used in a construction product, a construction system, and construction assembly. So it's very crucial that we consider this product stage raw material supply related emissions. So it includes emissions from mining, harvesting, processing of raw or recycled material, any emissions coming from the transport within the extraction site. It's not leaving the extraction site. So let's say you're doing extraction or processing of aggregate. All movement within that aggregate plant or quarry will be included in A1. Energy and water used in manufacture in raw material extraction is also part of this. So it applies to all types of construction, all materials, all products, including MEP systems. And it's also for both primary and secondary material sources. So maybe you have recycled steel, doesn't matter. Whatever is used in the processing of that also is included under A1. So A1 raw material supply, the emissions coming from that, imagine you're buying a cubic meter of concrete. You don't want to go and use first principles and go and calculate emissions coming from extraction of raw materials for your cement, then aggregate sand, water, it's mixing. You would, if you started doing that for first principles, it will become very difficult to do assessments. So we rely on published documents, which are called environmental product declarations, or EPDs. I'm sure all of you are familiar with this. The sector is relying on EPDs from which we read out our emissions. So there would generally be an EPD for cement, and then there may be an EPD for ready-mix concrete. You can use the appropriate material product and find out A1 from there, from that, literally a monogram from where you can calculate, or you can extract the carbon factor or carbon emission factor. So for materials products where EPDs are not available, you may have to go down to first principles, do an LCA, and calculate emissions that way. You must avoid double counting with modules A2 and A3, because A2 is transport, but that transport is outside of the processing plant over to the manufacturing plant, whereas all transport related emissions within the extraction plant are included in A1. So emissions must be allocated proportionally if materials serve multiple functions. For example, if steel is reused in a hybrid product, it should reflect the regional supply chains and energy sources. Biogenic carbon impacts, for example, timber, as per our standard, are calculated and reported separately and clearly labeled, because they're really acting as carbon store. So you don't want to include that in your in your A1 calculations. They should be, as I showed in the figure, they should be reported separately. The next sub-module within module A is for transport. This accounts for transport of raw materials and recycled materials to the product manufacturing facilities. So you've extracted some material that you need to use to create a construction product. The transport related emissions are all included in A2. So this includes emissions from vehicles such as road, rail, sea, inland waterways, loading, unloading, and intermediate storage if needed. Okay, so this A2 transport, which is sometimes also called internal transport or production related transport, versus we're going to see another transport module which relates to bringing these products, materials, components to the construction site. So more on that later, but A2 transport covers all your transportation related emissions from the extraction site over to your manufacturing plant. So A2 transport assumptions should reflect actual supply chains or use reliable average data. It must be separated from A1. So A1 and A3 are separate. Transport in between is calculated separately. If you're using multimodal transport, you need to account for each one separately. So something comes by ship and then is transported by trucks, you need to account for those separately. There are third-party databases. There is something, as I shared yesterday, the Global Logistics Association, which releases carbon factors. So they'll tell you, and you use those to do your calculations. The UK government publishes GHG conversion factors. Most national statistics offices, most government agencies are responsible for providing this kind of data, the carbon factors, which is also called secondary data or background data. Remember, when you're doing an assessment, you will need two types of data. One directly related to your asset or project, meaning quantity of concrete, quantity of steel. This is called primary or foreground data. And then you need conversion factors, emission factors, EPDs. Those are called secondary or background data. So when you combine those two is how you calculate the emissions for your buildings. So A2 is related to transport. Then comes A3, which is the actual manufacturing. So all emissions related to manufacturing and fabrication of construction products is also included here. Basically, if you have, let's say, offsite or a truss that is fabricated somewhere, that should also go under A3 manufacturing. So this include processing of raw materials into finished products, packaging, internal transport, assembly, energy and water consumption at the manufacturing site, emissions from on-site machinery, heating and industrial processes. This A3 manufacturing related emissions apply to all construction products, materials and components and MEP systems. So basically that's A1, A2, A3 is together called the product stage. We're looking at each and every individual product that's going to go into your building or infrastructure project. Similarly, A0 is called pre-construction, and that's for acquisition related emissions. So A3 manufacturing, generally, again, you're not going to go calculate fuel used, energy used, water used to create in the manufacturing plant the product that you're going to be using. Generally, we are going to rely on EPDs or environmental product databases. So as you can see, EPDs are central to whole life carbon assessment. We are going to spend time perhaps tomorrow separately talking about EPDs, their availability, their format, how to read them. I guess I'll give an example today also on how to read an EPD. Many of you would already be very familiar with it, but just to level set, we will look at that also today. So A3 is manufacturing, product stage done, pre-construction stage done. Then we are now moving into the construction stage where A4 transport emissions are basically all your emissions related to bringing stuff to the construction site. So applies to new builds. It also applies to any maintenance repair work that you will do in module B. Okay, so A4 transport is now bringing construction products and materials from your manufacturing or storage facility to the construction site. So let's say your project uses ready-mix concrete. Emissions from those ready-mix trucks are all computed under A4 or transport. It includes fuel used from freight vehicles, road, rail, sea, air, loading, unloading from manufacturing site to the construction site, any intermediate storage or transfer emissions. So if you decide to stage your material somewhere, you should account for that also. Obviously, key inputs for calculations are distance traveled, mode of transport, is it a truck, the fuel type used, the tonnage or the mass of the material and the vehicle itself. So A4, transport to the construction site, again applies to all products, materials, temporary works, and MEP systems delivered to site. You should use project-specific logistics data. So if ready-mix concrete trucks travel 17 kilometers to reach your site, you should use that in calculations. But as I said previously, we generally tend to make assumptions. We use EPDs that have built-in distance factors. So we don't go into very accurate calculations because remember, A4 is a tiny portion of the overall life cycle emissions that are going to come from our projects. Emissions, make sure you do separate calculations for half laden, full laden, empty return trips. All that should be calculated. We'll see how that is done. But I think generally, again, you do not go into that much level of detail if it doesn't warrant it. So emissions from worker travel, though, are not included here. They are part of module A5 or scope 3, if relevant. So they're part of module A5 and scope 3. Okay. So a quick example, this is adapted from US. So I did sort of a little bit of conversion. So you will see a bit of a problem in terms of units, but let's hope it all makes sense. So you're maybe working on a residential project in which you have maybe a slab on grade with concrete, a particular grade of concrete. The total quantity needed based on the thickness of the slab comes out to about 56 cubic meters. In the US, we have cubic yards, so converting truck capacity, let's assume each ready-mix truck, transit truck will have 8 cubic meter capacity. So you need 7 trips to bring this ready-mix concrete to site. Let's assume, again, hypothetically, the concrete plant to construction site is 24 kilometers one way. The fuel consumption factor you can get from the vehicle that is there, published data. So let's assume 1.3 is that fuel consumption factor. Each trip is 2 times 24 kilometers, so about 37.85 liters of diesel is consumed in each trip. Since there are 7 trips, you have 260 liters. Now you need to go and find out when that ready-mix truck is running, either every kilometer it runs, what are the emissions, or every liter of or gallon of diesel that's burned, what is that carbon factor? So in the US EPA publishes this. In the UK, the Statistics Office publishes this. Using that 2.68 kilograms carbon dioxide equivalent per liter of diesel, then gives you, for this material transport for your product, just concrete, you are using or you are emitting about 700 kilograms of carbon dioxide equivalent. Okay, so that's sort of how you are going to go about doing A4 calculations. But then there are companies that provide their
EPDs
with A4 values. So you do not need to even do these simple calculations. You can directly read it off your EPD and figure out A4 emissions using the EPD. Okay. Once again, I'm going to stop here and see if anyone has any questions. I'm trying to give you ample opportunity to interact, ask questions, give suggestions, share experiences, or correct me if I'm saying anything wrong. How are we doing on time?
Sir, we are moving as per the timeline, sir. So it's good.
Okay.
Like we can have 10 minutes break and then we can go ahead with the second session of day 2.
Okay. So I still have few slides, but I think it's best to stop.
Yeah, we can have a
You-
break for 5
You
minutes.
can have a break and then I'll continue from here. So I'll
Right.
need few more minutes to wrap this up and then move to the next session technically. But I think this is important. We need to, I'm going to try and bring an EPD, look at that, do another example, and slowly build forward.
Right, right.
Okay.
Now here it's 10:16, so let's break for 10 minutes. We can reassemble by 10:30, say 14 minutes break. Is that fine? So we have some of the delegates who are still available in physical mode. I am in my office only, sir. So,
Okay.
yeah, fine, fine. Because I am preparing for the second session, what I have to deliver.
Sure, sure,
Yeah.
absolutely, no problem.
So let's break for 10 minutes and quickly rejoin the session.
Okay.
Yeah. Bhagyashri, please look into this.
Sir,
Yeah, yeah. Just I'm saying that let's take a quick break. Let everyone take rest for 5-10 minutes. Let them have a cup of tea and ask them to rejoin in 10 minutes. Whoever are there in the office or in physical mode. Yeah.
sir, please don't leave the meeting. You can just turn off your camera and microphone.
Yes, thank you.
Yes, sir.
Okay, I guess we can start.
Yes, sir. We can start this.
Okay, excellent. So welcome back. We're going to continue with this. There's few slides more to cover before I jump into session 7 and 8, which are sort of combined, but there will maybe room for some questions, comments also from you, as well as perhaps look at some additional examples. So moving ahead after this example, last module, the most important module perhaps, even though it has a small contribution, is A5, which is the construction and installation process. Our standard, the RICS standard, breaks A5 into 4 separate submodules so that the calculations become easier and are easy to understand also. So A5.1 essentially are all emissions related to any demolition that's going to take place on the construction site. So any demolition, deconstruction of existing building structures, parts of that structure, including your transport, waste processing, all should go under A5.1. A5.2 is essentially construction activities, everything and anything to do with actual construction. So your concrete pumping, excavators, perhaps forklifts, or any other construction-related activities would be found under A5.2. Then you have A5.3, which is waste and waste management. It is production, transportation, storage, end-of-life treatment, and disposal of any material waste on site is included under A5.3. So 5.1, 5.2, 5.3 should be calculated. Again, many projects do not go into this level of detail, that they look at every construction means and method, every process, every activity, and use that to do the calculations. You would basically also have an option, so that's why we call it optional. A5.4 is your worker transport. So any emissions of site related to site workers traveling between where they are and from their to the site would be included in A5.4. Okay. So A5.1, pre-construction demolition. It basically captures emissions from demolition or deconstruction before new construction. In our standard, we specify that on the construction site, if there are any existing structures that are demolished, fully or partially, but within 3 years from the start of the new development, they should be accounted for in A5.1. So let's say you're building in a brownfield site, there are some existing structures, you break them, demolish them, remove all the demolition waste and all that good stuff, do the site prep. 6 months later, new construction starts. You need to include all the emissions coming from pre-construction demolition in your whole life carbon assessment for this particular asset that you're considering, or this particular project that you are calculating for. You then have all emissions related to transportation of the demolition waste from the site need to be included. Waste processing and disposal of removed materials needs to be included. This applies to new builds, brownfield sites, retrofit refurbishment options. All of those need to consider demolition. You should try and use the actual figures, but again, you may not have all the information available to you to do the demolition emissions, waste transport, and disposal related emissions. Our standard provides, in case data is not available, you can apply a default rate of 35 kilograms carbon dioxide equivalent per square meter of gross internal area. So these are based on London specific UK case studies. As a rule of thumb, you can take 35 kilograms carbon dioxide equivalent, measure your floor area, and multiply. That will become your A5.1 emissions calculations. Obviously, you want to only do that when there is demolition as part of your project and assessment. So try and report separately within A5 as part of upfront carbon. You can have A5.1 reported separately. Any recoverable benefits from reused materials should obviously go into module D and as part of D1. So let's say you had some structural steel beams and so on. They may be reused somewhere else, maybe within the project or within another project of the organization. You need to account for that appropriately in module D. We will cover situations where you have this kind of recoverable benefits, reused materials, where they should be accounted for. We will be describing those also. A5.2 relates to construction activities, so it covers all on-site construction installation processes. It's all your site prep, site setup, mobilization, groundwork, your temporary facilities or utilities, on-site storage, transportation, temporary works, assembly of products, materials, lifting of stuff, pouring of concrete, compacting. All those construction means and methods should be accounted for in A5.2. All energy and water use for site offices, heating, cooling, lighting should also be included in A5.2. So obviously, if you are going to go to a level of detail and doing these calculations, if you're, let's say you have scaffolding, or formwork, you have tower cranes, you are going to only utilize emissions from those temporary equipments that are used for your project, because there's going to be reuse also. So make sure that that is accounted for. Once again, if you don't go and want to calculate from these first principles, every construction means and method, because there is so much data available on assessments in the UK, rule of thumb says you can add 40 kilograms of carbon dioxide equivalent per square meter of your gross internal area if this is a building, unless more accurate project data is available. So again, you can make these simpler calculations if you want to for your project or for your asset, for your assessment. So encourage contractors to identify and mitigate 80% of anticipated site emissions before work begins. So for example, switching from diesel to electric or hydrogen powered equipment. And it's happening. So like in the US, contractors are trying to move away from diesel operated construction equipment, moving to electric perhaps, and therefore already reducing the site emissions. So A5.3 is to do with waste and waste management. So it captures emissions from site-generated waste during the construction process. Remember, A5 is construction and installation process-related emission only. So any wasted construction material, which is actually a pretty bad thing, we shouldn't be wasting construction material. The material that came in didn't get installed, emissions related to that. So that waste, transport of waste offsite, waste treatment, recycling or disposal, packaging waste, default 32% of site waste mass if no data is available. So again, you can utilize some thumb rules for packaging waste, for example. Key considerations only include materials not installed in the asset. Deconstruction and installation emissions for wasted items should be considered as zero because you just sort of brought them and moved them out of site. Manufacturing waste from off-site construction. So let's say you're using modular construction, which is maybe factory-built components, maybe wall panels, your trusses, maybe bathroom pods. The waste that occurs in the factory should be part of A1, A2, A3. That is still considered the product stage, not the construction stage. So minor clarification there. So if your site, your construction project is going to use extensively modern methods of construction, such as prefabricated panels, all manufacturing waste will go into A1, A2, A3, and not A5.3, this particular submodule within module A. So again, there are various ways of calculating this. Our standard tries to give you as much information as possible for waste and waste management related emissions. Broadly, A5.3 related emissions are calculated by a waste rate. I think most cost consultants, folks who know how to do quantity takeoff, would have these waste factors. So let's say ceiling plaster, interior wall plaster, when you pour concrete, when you do woodwork, there is always some percentage of wastage, and it's generally known to experts who work in this field. And then A5.3 emissions are equal to the product of the waste rate multiplied by what's called the site waste treatment emission factor, or EF. So the standard RICS standard gives the waste rates. There's a whole table that, for example, says for in situ concrete, there will be 5% waste. For brickwork, assume 6% waste. This is obviously more UK-centric right now, but as we have more and more data, these can be global or regional numbers also. So if you don't have site-specific data, use the tables. Otherwise, you can use site-specific data also. So disposal scenarios that determine the site waste treatment emission factor depend on what you're going to be doing with that waste. So is it going to go to landfill? It's going to be incinerated? Is it going to be reused on or off site? Each one of those will have different emission factors. You encourage accurate tracking of waste types. That probably connects to other enablers of decarbonization, such as lean principles. If you're using lean on your construction site, then you are always focused on reducing waste. And if there is waste, you track the waste type so that you can find the root cause and make improvements or changes. And then you have the actual project waste rates, which must be reported upon project completion. Many jurisdictions require you to fill a waste card or piece of information that tells you what happened, where is this waste headed, and so on. So if you look at the standard, you will see WR provided. It's a much longer table. I've just given you a brief snapshot of what typically is considered as a waste rate for your project. And then once you have this information, you can do the EF, which is the site waste disposal carbon factor. If the waste that you have is going to go to disposal, let's say to a landfill, or is going to be burnt, then your waste factor is determined from A1, A2, A3, A plus A4, and then the C module, which we have not yet discussed, C2 for transport, C4 for disposal into waste, into landfill. So depending on how you are going to be using the waste, the emission factor changes. So EF changes. If this is going to be reused, recycled on site, obviously then there is no transport. So you have A1, A3, A4, and C3. If it's going to be reused, recycled to on another project, you will have C2, which is end of life transport emission. So that's how this is structured, and you then calculate A5.3. A5.4 worker transport is generally optional, but let's say you have a huge infrastructure project in which workers have to commute a significant distance, especially maybe you provide the company, the contractor, the construction company provides transportation, then you should calculate worker transport also. So it accounts for emissions from site workers commuting to and from site during the construction phase. It's relevant for large infrastructure projects, remote or dispersed construction sites, and those specific situations where you have those emissions related specifically to construction worker transport. I haven't come across large projects where this is calculated and reported, so that's why it's considered optional. Again, you can use approximations, you can do daily commute rates, number of workers, multiply by vehicle type. Most governments publish emissions per kilometer travel for various vehicle types. So use those to come up with emission calculations for A5.4. So generally it is excluded, it's considered negligible, and it's optional if it's a building site in a city center. You do not provide transport for your workers. They may be commuting on their own, but so that's omitted, not included. So maybe before we jump, and this basically concludes the calculation workflows and guidance, mandatory requirements from the standard, from the RICS standard. You will see similar workflow calculations even in EN 15978 or any other global standards. The thumb rule, the numbers like 35 kilograms carbon dioxide equivalent per square meter of GIA, that may vary, but the steps, the calculation process should remain the same. Okay, so module A calculations are done this way. We're going to look at module B, C, and D separately in another session. But before we close this, I'm running a little bit behind, but I do want to look at this example. So you have module A example in which you're using, let's say, again, a residential project in which you're using 50 cubic meters of M30 grade concrete in a slab. Okay, you are the assessor. You have to do calculations for A1, A2, A3, A4. That is your product stage and the transport from the ready mix plant to the construction site. Okay, so you're basically going to be doing A1, A2, A3, A4 calculations. In this instance, because this product, which is ready mix concrete of a given grade, it's not too difficult to find the EPD. Now, there could be a situation like in India, EPDs are not plant specific generally, I think. In the US, you can actually search for a plant, maybe 10 miles from where I am right now. You can pick that specific plant and get the EPD of concrete that they deliver to your location. Obviously, it's going to be more accurate, but in the absence of that, you can use regional averages, industry-wide EPDs. They're better than doing your LCA calculations for ready-mix concrete in detail using your own calculations. Okay, so here the role of environmental product declarations, EPDs, becomes extremely crucial. So I think somebody asked yesterday, how can you promote the development of the ecosystem for WLCA calculation in the country? One way to do that would be to enhance the availability of EPDs in the region, in India. So the government can run a program to increase the number of EPDs available, involve product manufacturers, and request them to add more and more EPDs, maybe by region, by location also. Okay, so let me quickly stop sharing. Okay. Give me a minute while I load up the PDF. Just let me swap the screens and then we'll be ready to go. Okay. Sorry about that. Okay. Okay. Here we go. Okay. Let me know when you can see the PDF. Okay. Thank you. Thank you, Dr. Nakwale. So this is an example EPD. You may have seen it. You may have used it before. This is how an EPD looks like in PDF format. Obviously, and we're going to discuss that in a session on data standards, carbon emissions data. So that's tomorrow around this time, we will be talking about digital format of EPDs. PDFs are very flat. If somebody has to read it, even though you can use AI tools these days to automate the reading of an EPD, but there are better formats called OpenEPD and others that can get you this information digitally. So I'm going to use this as an example to share and level set. Some of you already probably are experts, but I'm going to sort of do a very basic example here. So this is an EPD produced by JSW Concrete, okay, for ready-mix concrete. Few things to note, and I've tried to highlight those. You can see here that it is a verified EPD. It is still valid because it's still 2027. You want to make sure that any EPD you use, it has the validity date beyond the project that you're working on. It's for India. Okay. Obviously, there's a lot of information. The tool, the software that is used to develop this EPD is Gabi, which I think we will be covering again tomorrow after lunch. So you will see this is for ready-mix concrete manufactured at these locations. But we are going to treat this as a regional EPD and use it for a project, let's say, in Nagpur also. So some more detail. You should try and see what ISO and EN standards they use for preparing this EPD. Very important to check what's called a PCR. A PCR is essentially a product category rules. So when developing an EPD, you need to have basic principles that tell you how to prepare the EPD. So that PCR, reference PCR, is crucial. The product category rules used for this are for ready mix concrete, which is good. And this particular EPD will cover M7.5 to M60 grade concrete. The EPD, very interestingly, I have seen EPDs that only give modules A1, A2, A3. But this EPD has A4 also. And obviously, very few current EPDs give C and D module emissions also. For today's example, we are not looking at C and D. Maybe we'll look at those when we cover how the workflow and calculations for module C and module D. Okay, but always important to find out what the system boundary and product stages are. So this is how they have laid out the system boundary. This is basically life cycle analysis done on the ready mix concrete when preparing the CPD. So they are looking at all raw materials. They are looking transport to factory, mixing concrete, end of life, module C. They also tell you the emissions that come from demolition and waste processing. So you have your end of life calculations also, but we'll consider them later. Very important to make sure that the declared unit is identified. In this case, all emission values in the EPD are going to be for 1 cubic meter of ready mix concrete of a particular grade. And then, as per EN 15804 plus A2 2019 version, these are the environmental indicators that are included in this EPD. So they do give GWP total, GWP from fossil fuel, GWP biogenic, GWP from land use change related, and so on. So many more indicators that we are going to use. For our assessments, we currently focus on GWP total. So this first row is what we are going to be interested in. So you can see more details. Obviously, you can take time to read these. They have included upstream transport. Remember, during the product stage, any transport that takes place in the manufacturing plant, extraction, all of that is A2. But surprisingly, they give downstream transport also. But there's a little drawback, which is that they do not say what is the distance that they have assumed between the ready mix plant and site. They can use an average distance. They do mention 50 kilometers, but that's for the transportation of the waste. When you demolish that concrete and send it for maybe C&D waste. So it's unclear in this particular EPD what is the distance that they have used in calculating A4. So they should technically tell you, like in the UK, I believe it is about 16.7 miles is the average distance assumed between a ready mix plant and a construction site. Yours may be 25 miles or 10 miles, but the data that they provide assumes that average transport distance. In this case, I couldn't find it, which is not a big deal, but they've used some average distance between the plant and a typical site. So beyond that is where they tell you, wherever you see the X, you have values. And wherever there is this M&D module not declared. So they don't declare A5. They do not declare any use stage. but they do declare in their EPD C1, C2, C3, C4, and module D. Module D is going to be largely zero because the concrete you break up, in this case, is being sent to landfill, perhaps. Then you will have numerous tables by grade. So for your 7.5 ready-mix concrete, the number that we are interested in, or the row that we are interested in, is the first one, total GWP. We are not going to look at acidification and others, but obviously you can. So you have 96.8 kilograms of carbon dioxide equivalent per cubic meter of 7.5 grade concrete for modules A1, A2, A3. The value for A4 is given. So this is what you use in order to calculate your projects A1, A2, A3, A4 using this EPD. So I think in our case, we are doing 30. So page, I believe 22. So you have 1 cubic meter of M30 grade concrete. Oops, not 22. It should be 20, page 21. 1 cubic meter of M30 grade concrete. GWP A1, A4 is highlighted here. So you can see the value of A1, A2, 3 emissions. You have 50 cubic meters, so you're going to multiply. Similarly, for A4, you have for 1 cubic meter, you're going to multiply again. So that's how module A is generally calculated. You search for an EPD. Obviously, the problem is going to be for locations where there is no EPD, locations for which certain products don't have EPD, and there may be lots of other in-between cases. That's where the challenge of data comes in. But as the practice improves, more and more data gets collected, we would see that this issue can be overcome. Okay, before I stop sharing, let me pause and see if anyone has any questions. Has anyone come across more ready-mix concrete? Which other manufacturers or concrete producers have EPDs in India? So if I were to search for EPD for Delhi or Nagpur for ready-mix concrete, how easy or difficult would it be for me to find it? Anyone? Okay. I'm going to stop sharing. Okay, let me bring up my slides again. Okay, give me 1 minute. Okay, I think my slide should appear now. So you will notice that we basically took the numbers from that table, which was, I believe, page 21, A1, A3, 245 kilograms carbon dioxide equivalent per cubic meter. That was the declared unit. A4 is 3.63. You have 50 cubic meters. So basically that's your A1, A2, A3, A4 emissions from concrete on your projects, on that particular project. So very simple example, but it does highlight the importance of all the data that's needed. So if you were doing a decent size office building, for example, one key thing that you would need is obviously the quantities. You also want to make sure that the quantities and the units match with the EPD that you're using. So maybe you have 50 cubic yards of concrete, but the EPD is for cubic meter of concrete. You need to make sure that the units match. The grade should be matching, and essentially utilizing all this information. Quantities, specification of materials, and the right EPDs would be required in order to do emission calculations, especially for embodied concrete upfront during construction. Okay, so that once again, I think this particular portion of today's topic is complete. I'm going to give you another chance to see if you have any questions. Mm-hmm.
So Vaidik ma'am is asking, what should be the ideal frequency of recalculating EPD for the product?
Could you repeat that? It was sound is a bit low.
What should be the ideal frequency of recalculating EPD for a product?
So a manufacturer would get the EPDs are issued. I think they are good for 3 years, 3 to 5 years, but it will say when they were issued, until what period they are valid, and you should not be using expired EPDs. It may depend from product to product, but I think typically it will be 3 to 5 years. And more manufacturers are being encouraged to EPDs. So it's like your labels on the food that you buy. Let's say you buy a packaged food. In most countries now, you have to declare calories, sugar, salt. Same way you are declaring through these EPDs the GWP values for the product that you're selling. So as sustainability practices take hold, it's in the manufacturer's best interest to provide the best, most accurate, most reliable, up-to-date EPDs. If you have obviously a low carbon product, it makes sense for you to get an EPD so that you can demonstrate that it is a lower carbon emission product that you're trying to market, and provide to the designers that information so that it can be adopted on various projects. Okay. Any other questions?
No, sir.
Okay. All right. So let me stop sharing. Let me close this presentation, start the next one. Okay, almost there. Give me 1 minute. Okay. You should be able to see my next slide or slides. We are going to now move to, if you look at the agenda, we're going to move to topics that are related to infrastructure projects and related to another standard that is closely linked to WLCA called ICMS. It's the International Cost Management Standard. And there's a reason why we want to connect WLCA to ICMS. Okay. So let me start with describing what ICMS is. So ICMS is the International Cost Management Standard. It's an international standard to bring about consistency in presenting life cycle costs and carbon emissions. So that statement itself tells you everything. It is the first standard globally available in which you can report carbon emissions and costs, life cycle costs, in an integrated fashion. Why? Because no one is going to, I shouldn't say no one, it's going to be very hard to reduce carbon emissions, improve environmental performance of our projects and assets without keeping an eye on the costs. Since we are talking about whole life carbon assessment, we should not be just looking at life cycle, shouldn't be looking at construction costs or capital cost alone. We should look at life cycle costs. So in order to decarbonize, we need to search for cost-effective options also. You can't just decarbonize at any cost. So most prudent decision makers are going to search for a cost-effective way of decarbonization. Okay, so ICMS is a global standard that was created by the ICMS Coalition. ICMS Coalition was in fact launched 10 years ago in DC at the IMF. So the coalition was created as an independent standard setting entity which has a standard setting committee. I am currently the chair of the standard setting committee. The idea was to bring together 27 or so independent experts from 17 countries to write the standard, which was originally called International Construction Measurement Standard, but now it has been renamed and is called the International Cost Management Standard. So the ICMS is again a freely available standard that you can download from the ICMS website, which is provided below on the slide. We are going to be sharing with you all these slides in PDF, I believe, so you should be able to get this information. As you can see, there are about, I think, 50 global not-for-profit professional bodies who have come together to create this standard. You will notice RICS is one member, RIBA, the Royal Institute of British Architects, is another one, and Indian Institute of Quantity Surveyors, IIQS. As you will see on the left side of the screen, is another entity that's part of the coalition. So you will see so many coalition members who have come together to create this standard. We have industry partners, so major global cost consulting and general consulting firms are supporting this standard, and there are many more. This is just an example of the market adoption. Several governments and clients are supporting ICMS also. The national highways in the UK are supporting the ICMS standard. A couple of years ago, we had more adoptions. So the Irish government actually has adopted ICMS in their National Development Plan Delivery and Reform Framework. So you see these two ministers have given quotes and announced the adoption of our ICMS standard. But what I want to highlight here is adoption of ICMS, its availability in Building Transparency's carbon calculator, which is called EC3, or embodied carbon in construction calculator. We are going to be running a demo session on EC3, I believe, either tomorrow or the day after. So you will get to see a little bit of what EC3 can do in terms of calculating carbon, but also cost, because they have adopted ICMS. Similarly, some of the Autodesk tools also have adopted ICMS. So you can see cost and carbon is getting integrated. This is the third edition of ICMS, was launched in 2021. It basically is an open source document available online, and again, mandated for our members of all coalitions. So I think if you look at it, maybe there are about 350,000 global members who are using or can use ICMS. So we've translated ICMS into simplified Mandarin, Japanese, Italian. I think a Spanish version is also available. There is an ICMS explained guide that you can use to understand what the International Cost Management Standard. So it's like a guidance further on the standard. But here is what we have done. So we've created an international cost management standard in which we have developed a high-level taxonomy and format for classifying, defining, recording, analyzing, and presenting life cycle costs and carbon emissions associated with constructed assets. So what we have done is we've created essentially a taxonomy which is called ACROM. ACROM stands for acquisition, construction, renewal, operation, maintenance, and end of life. So something familiar, similar to the information modules that you've seen in 5978, as well as the RICS WLCA standard. Using this taxonomy, the cost and carbon are reported. So you have an asset for which you've done emissions calculations using, let's say, the RICS WLCA. You can use ICMS and combine the reporting of the emissions under the ACROM hierarchy alongside the cost. So let's say you do an assessment with one option, you can present that emissions and cost together. Then you run the second option and you can present its cost and its emissions, so that then you can compare which one makes more sense. The ICMS system also includes something called project and asset attributes and values. So imagine you've a building project, maybe a school building project, in which you have various attributes. So it has maybe 5,000 square meters, maybe it has 3 levels, maybe it is in certain seismic zone, certain climatic zone. All those attributes are given. Alongside that, you do WLCA and cost calculations using one taxonomy, the ACROM. You report the life cycle cost and life cycle whole life emissions for your building. If you start building that database and you have hundreds of school projects with their features or attributes and values provided, you can now start comparing, finding what's called the reference class, and then use that reference class to forecast for your current project what would be the cost and emissions. So that's the benefit of having a unified taxonomy called ACROM, and then having a list of project and asset attributes and values. So this results in the integration of life cycle costs and carbon emissions. So if you look at the WLCA standard, it's very good at producing module A, module B, module C, module D emissions. If you combine it with life cycle costs from ICMS, it becomes even more powerful because now you can make cost-effective decisions for decarbonization. So ICMS, as I told you, was first, we started working in 10 years ago in 2015. The first edition was released, I believe, 2017. And then the second edition was released in 2019. And then the third edition, which is the current edition, is released in November 2021. The first edition had only capital cost. So it was a classification system which all projects could use to report construction costs or capital costs. Right after that, we realized there's no point. We need to provide life cycle costs. So acquisition, construction, renewal, operation, maintenance, end of life costs were released in the second edition. And then soon after that, in the third edition, we combined life cycle costs with life cycle carbon emissions so that both cost and carbon can be reported simultaneously. So honestly, in the early stages of ICMS, when we were trying to go and get it adopted, implemented by construction companies and by perhaps many of the clients, including public sector clients, it was a difficult uphill battle because costs are generally confidential. They are not released openly, publicly. But ever since 2021, when we launched the third edition in which we incorporated life cycle carbon emissions, made them transparent, because remember I said earlier that if you're doing checking whether your building is performing on your carbon targets or not, you got to make it available to people. You need to report it. So you can't hide carbon emissions. So with the third edition, we overcome some of that hurdle, and there's significant adoption of ICMS now. Yeah. Because ICMS allows you to do life cycle cost and carbon emission reporting, ICMS is only a reporting framework. It doesn't have any methodology in terms of WLCA. That is separate. But it allows 19 types of entities. We have created templates for 19 types of entities within ICMS. So with the third edition, you can have all types of buildings, and you can also have all types of infrastructure, or 18 types of infrastructure assets that can be reported under ICMS. So by combining WLCA and ICMS, we have opened up the possibility of reporting, calculating, reporting roadways and runways, railway networks, bridges, tunnels, water treatment plants, pipeline projects, wells and bores, power plants, chemical plants, refineries, dams and reservoirs, mines and quarries. And you can see from this list ports, waterways, and so on. We are also adding whenever possible, we are adding more project asset types or entity types. So for right now, work is going on transmission projects. So those transmission projects will also be added. So you can see WLCA, ICMS together work not only for buildings, but also for infrastructure assets, yeah, which is really the crux and the core of this GIAN workshop. Within ICMS, you can practically do all building typologies. You can have residential, office, commercial, shopping center, industrial, and the list goes on. It is also possible to do both new builds, temporary and retrofits or adaptations. So again, works very well with WLCA, where you can do a new build or an existing building. You can also create projects and sub-projects. So you can have large or complex projects that can be subdivided for cost and carbon emission reporting into sub-projects and described by a single set of project attributes and values. You can also capture large portfolios, programs through this approach of sub-projects. So let's say you have a transportation network that can be your master project. Within that, you have station buildings, roads, rails, bridges, tunnels. They can be sub-projects. You can do life cycle cost and carbon emission reporting by each one of these sub-projects. So we have additional piece of information then that can be added to your cost and carbon information. These are, as I explained earlier, are called project attributes and values. So you have construction program, procurement, life cycle, carbon emission related attributes. Why is this important? It's very useful because for benchmarking purposes. So if you have a school building, its features, its characteristics, its attributes and values, if they're captured alongside the assessment of life cycle cost and life cycle emissions, you can then use it for benchmarking purposes. The taxonomy that's used in ICMS is pretty straightforward. At level 1, you have your projects and sub-projects as I had just described. At this level, you are also declaring your project attributes and values. So I'm a construction company. I want to report using WLC and ICMS cost and carbon. I can provide my project. Sub-projects are optional. And then whole list of general entity project specific, life cycle specific, carbon emission specific attributes and values. Below that is level 2, which is called the categories. They're common for cost and carbon, and that's the beauty, because as you report your categories, you're reporting both cost and carbon simultaneously. Level 3 is called groups, again, both for cost and carbon. Below that is level 4, which is your subgroups, and again, applies to cost and carbon. These are not mandatory. So minimum requirement for WLCA and life cycle cost reporting under ICMS is levels 1, level 2, and level 3. This is how the taxonomy looks like, and that's how it gets the name A Chrome across. So you have whole life cycle costs and carbon emissions. That is the goal of producing with ICMS so that we can have a consistent hierarchy. So you have your non-construction costs and carbon emissions. Remember, we had acquisition or pre-construction. That's sitting right here. Then you have your module A emissions and related costs. They come sit under C or Chrome, which is construction costs and carbon emissions. Then you have renewal costs and carbon emissions. That is the R in the A Chrome. This again connects back to WLCA as well as the cost. The goal here is to come up with a taxonomy which is integrated for both cost and carbon emissions. You have operation costs and carbon emissions. You have maintenance costs and carbon emissions. You have end of life costs and carbon emissions. So these are your categories. So this is that level 2 that we just saw, which were the categories. So A, Chrome are the categories of ICMS. Below that are your reporting groups and reporting subgroups. So that's your level 1, level 2, level 3, level 4 hierarchy of ICMS. In more detail, this is how it looks like. All boxes that you see in green are boxes where you're required to report both cost and carbon. So the boxes under A, which is your acquisition or pre-construction costs and carbon emissions, remember, they only apply to infrastructure. They are generally considered optional for buildings, so they're not seen as green here, but they are included. Then you have construction costs CC and construction emissions CE. They use a single hierarchical breakdown. So these are your categories, A, Chrome. The groups that are used underneath construction costs and carbon emissions actually are shared between renewal costs and carbon emissions and maintenance costs and carbon emissions. So these have demolition as 0, 1. Remember, we just talked about demolition in module A. You have substructure, structure, architectural works or non-structural works, your services and equipment, surface and underground drainage, external and ancillary works, and whatever is under preliminaries or your temporary works, those kinds of things are included here, and your general requirements. And you can see basically that's the hierarchy followed for C, R, and M. For the operation costs category, carbon category, you have a different hierarchy that is used. These are the groups: cleaning cost and carbon, utilities cost and carbon, waste management cost and carbon, security, ICT, and so on. And then you have your end of life, which has a separate hierarchy, decommissioning and decontamination emissions and costs, demolition and reclamation costs and carbon emissions, and so on. So the idea here is this high-level taxonomy that combines cost and carbon and allows about 19 different project types or entity types to be reported. If everyone follows at a high level, obviously you can have much more detail below this, both for your cost and for your carbon. But as long as people fix level 1, level 2, level 3, we can start comparing, benchmarking, baselining our cost and carbon emissions. Okay, so the goal is to create this taxonomy and use it to basically not only integrate cost and carbon, but also bring some consistency in terms of inclusions and exclusions for maintaining your assessments for all the projects and programs that you may have. So in order to accomplish this, it was not an easy task because different parts of the world use different classification systems. Think of the CPWD schedule of rates, or those familiar with UK system, think of it as Uniclass. If you're familiar with North American system, think of it as master format or Uniclass. or any other system such as work packages, work breakdown structure. Different parts of the world treat their cost breakdown, carbon breakdown in any of these categories. In the UK, you will have elemental classification systems. So you'll have your beams, columns, and so on. In the US, Canada, and other parts of the world, the classification is trade-based. So concreting contractor or concreting trade, brickwork trade, and so on. It is not elemental. We got to make ICMS such that in any of these different types of classification systems, ICMS can be mapped. So that if in India you're using maybe a trade-based classification, and in the UK, the predominant one is an elemental classification system, for example, using Uniclass, you are still able to, at the high level, maintain the same map. So that everyone reports, you can have not only regional, national benchmarks, but you can have global benchmarks also. WBS and work packages are equally important because, for example, the national highways, earlier used to be called Highways England. National highways uses a work package or work breakdown structure-based classification system. So if we are able to still utilize WBS and map it back to ICMS level 4 and maintain level 1, level 2, level 3, again, we are creating global consistency for making this happen. Okay, so a typical ICMS report with only life cycle cost could look like this. So this is a sample report by one of our partners. It's for an office building, I believe in the UK, maybe in London, in which you are evaluating options on what to do with this existing building. So these are alternative 1, this is alternative 2. You can see that somebody has estimated life cycle cost. They have found out the acquisition cost, construction cost, renewal cost for 30-year life cycle, then operation costs, including cleaning, utilities, waste management, and so on that you saw over there. And then end of life costs, as I showed previously under the ICMS taxonomy. So you can now compare alternative 1 to alternative 2, not just simply looking at construction cost, but looking at the life cycle cost, and pick the right alternative that works for you. Since we will be reporting carbon emissions across the same hierarchy, you can now easily see how decision makers can evaluate 2 options. One may be low carbon, one may be business as usual, not only their carbon intensity, but also the cost of each alternative or each design option. And then from there, you can make a decision which one to pick. So basically, you will have this kind of a report. So this is another sample report from one of our partners. It's in the GLA, the Greater London Authority. They have used a tool called One-Click LCA, which several of you would be familiar with. They have used energy modeling in the UK called SAP10, which is changing soon. But the point is, for the building, you are able to calculate carbon emissions. Remember, the pre-construction A0 carbon emissions are negligible for buildings. So that's noted here. But then to compare these options, you have the tons of carbon dioxide equivalent for construction, renewal, operation, maintenance, and end of life. And if there are any benefits and loads, module D, beyond the system boundary, you also calculate and put them there. So basically what we are doing is summating under each category: acquisition, construction, renewal, operation, maintenance, end of life, all the ICMS groups and subgroups to bring up these values. So imagine now you had simultaneously life cycle cost. You can now make a decision which option would work best for you. So ultimately, the goal is to prepare an organizational or sector level benchmarking system using ICMS. So let's say you have hundreds of projects. In each one of those projects, you are able to do WLCA, use ICMS to classify your cost and your carbon, and you continue to store that in a database. If you have this kind of a database that uses the ICMS mapping, you have both new builds as well as existing assets. You have your historical project and asset data that you map into ICMS and store it in the database. This is the benefit that you can have within your organization or out broadly in the industry. Since you're storing your carbon emissions life cycle costs in that database by project attributes, you can search and find a group of historical projects which are relevant for your current project for which you're doing the estimate. So in that case, you're able to have the early cost and carbon advice, because now if new school building has to be created, you can simply go into this benchmarking database and find out what are the benchmarks, what are the baselines based on which you can give early cost and carbon advice to your client or to your senior leadership team. Then you can make investment decisions. You can streamline project selection and initiation. So maybe you can consider cost and carbon and decide not to move forward because that project doesn't make sense. You can select options with a whole of life perspective. You can measure performance. You can show progress against targets. You can benchmark life cycle costs and carbon emissions, enhance cost certainty using this kind of a database. Okay, I'm going to pause here and see if anyone has any questions. Okay. So there were some difficulties in combining cost and carbon into an integrated framework. If you look at the life cycle cost breakdown, and if you look at the whole life carbon assessment framework within which you have those modules A, B, C, and D, what is called life cycle cost is technically same as the whole life carbon in the WLCA. So you will see that it is not the whole life cost as per ISO 15686, which is the life cycle costing standard. The whole life cost includes externalities, non-construction costs, and income. Okay, so we are basically mapping life cycle costs with whole life carbon, because in whole life carbon taxonomy, the module D is excluded. So basically, what has been done is for integrating ICMS and WLCA, this map has been created. So you will see A0, which is the acquisition cost, which is optional in buildings, required for infrastructure projects, can map to either A1 or C2, the construction category of ICMS. Product stage, transport stage, construction process, all neatly map to in the achrome hierarchy to C. B4, B5 connect to renewal in the ICMS category architecture. B1, B2, B6, B7, B8 connect to O, or of the achrome, the operation. The B2, B3 connect to the M in achrome, which is the maintenance. C1, C2, C3, C4 connect with the end of life category in the achrome category list. And module D, benefits and loads beyond the system boundary, connect to externalities as shown here. Okay, so that is what's needed to bring ICMS and WLCA together. So if you look at the ICMS third edition, this is the more detailed mapping that has been provided. Okay, so the acquisition carbon emissions, where significant obvious infrastructure projects connect to A0, which is the pre-construction emissions. A1, A2, A3, A4, A5 all get combined and mapped into the construction carbon emissions category alongside the construction cost. The renewal emissions are connected to B1, B4, and B5. And below that, you can see the hierarchy of the groups. B6, B7, B8, which is the user carbon or generally for infrastructure, can be connected back here. And then you have your maintenance carbon emissions, which are B1, B2, B3. So use, maintenance, and repair. And then end of life very neatly sits under C1, C2, C3, C4, which are the demolition, deconstruction, demolition emissions and costs, transport to disposal facility costs and emissions. And then you have waste processing for reuse, recovery, and recycling, which is C3. So all costs and emissions related to that. And then you have your disposal, which is your C4. So that's the detailed mapping between WLCA and ICMS, so that you can utilize this kind of a structure to report cost and carbon for your projects and assets. Okay, so ICMS also provides a functional unit. Remember, we said for buildings, it's a gross internal area, GIA, even though there are discrepancies on how we measure GIA. ICMS provides that kind of functional unit for measurement, or functional equivalent for benchmarking and measurement. So if you look at ICMS, this is how one of the reports looks like. We would generally have meter square of site area. So these are the length of the site boundary. These are the functional units that are provided in ICMS. So you can see that in terms of dollars per square meter of site area, but you can then also see kilograms carbon dioxide equivalent per square meter of site area. So everyone is now using the same functional equivalent, the same unit. So benchmarking, comparison, and baselining becomes much easier. So more work is needed. So the ICMS standard setting committee is right now working on figuring out what these additional functional units can be. So if we can go down up to the group level, we can come up with a uniform functional unit. Let's say at the substructure level, the structure, the services. So you can start reporting your cost and carbon across that functional unit. Again, brings benchmarking below one level. So not only you can say for school buildings, there's a benchmark for cost and carbon, but you can also say at the structure, substructure, services level, there is a cost and carbon benchmark. So you can give better early advice to your clients or to your leadership team. So this is one of the reporting formats. You can see ICMS breakdown used here. You can see that I don't know whether how readable this is, but you can see the demolition site, the all other substructure with level 2 here, level 4 ICMS code listed here, and then all modules A0, A1, A2, A3, A4, and so on reported by column. So we are currently working on utilizing this approach of using ICMS as a high-level taxonomy, using the whole life carbon assessment professional standard and other classification systems. We are building this built environment carbon database, which has entity level benchmarks and product level benchmarks also. So essentially, this built environment carbon database can have a whole number of projects, but it can also have EPDs for various products. I think some databases have like 200,000 EPDs. If you go to EC3, I think they have that many number of EPDs stored. So this kind of a benchmarking database for assets and products can go a long way in helping create a WLCA ecosystem for the region where you are operating. Okay, so that takes care of that. I'm going to stop sharing. Okay, pause here. We have covered quite a bit of material. I'm going to take you into ICMS live into the document and show you some of these things. But before that, I had a question, or if anyone had any questions, comments, or suggestions, I'm more than happy to talk about that now. No questions? I see Professor Aligaonkar off mute. No, he's still on mute, sorry. Anyone has any questions or comments? I do need...
Sir, this is...
Yes.
Sir, am I audible?
Yes, you are.
Sir, so yesterday also we saw some standards, methods. Today also. What is common in them is the approach for calculation of carbon emission, I think. And the actual method will change scenario to scenario. So if I am using for my own project two different methods or standards for calculating carbon emission, how can I compare it?
It's a sort of a good question and advanced topic. What we are also doing is we'll be sharing, I think, in one of the advanced topics, there is something called harmonization principles. So while I'm using for somebody's using a different standard, I'm using a different standard, how can I harmonize the underlying methodology? So we have identified 7 dimensions of harmonization. If you can apply those, then you can actually have um, some comparison possible. I'll give you an example. In Germany, when you do whole life carbon assessment, for buildings, it's regulated that you will do it for 50 years. In the UK, it is mandated that a building would be, WLCA would be run for 60 years. That is the reference study period that we discussed yesterday. Now, how can you compare these two? It's possible if you declare in your assessment what was the number of years that you used, the RSP. And secondly, if you can annualize your emissions, right, rather than giving one number, you can give annual sort of cash flow, carbon flow, kind of an annual number, then you're able
Right.
to compare. If you go back and look at EN 5978, it shows you how to extrapolate emissions from 50 to 60 years. So there are ways of harmonizing and aligning standards so that comparison is possible. I hope it answers your question.
Yes, yes, sir.
Okay.
So a question arises because in India right now there are no clear guidelines, I think.
That's right. Yeah. Even
So
though I
if
came
someone has to
across.
do,
Uh-huh.
they have to rely on a standard which we are
Mhm.
adopting to our situations. That is why there
Correct.
was a doubt in my mind.
Absolutely. Yeah. So there are many regions where there is no WLCA standard, very limited EPDs. It's a pretty complex topic right now because of not too much in practice. There are not many practitioners who are using this approach. So in those cases, most people will resort to using an international standard, which is a good starting point, but obviously it doesn't fully connect to the local construction methods, maybe local climate, local conditions and customs. So it's an ongoing debate on how best to manage that situation.
Right. Thank you, sir.
Uh-huh.
Very insightful, nice lectures.
Thank you. Thank you very
Thank
much.
you. Thank you.
I'd like to hear from others in the room, maybe, or in the virtual room. Anyone else has any questions?
Yes, so participants, if you are not able to unmute yourself, you can put the questions on the group, WhatsApp group. We will read it and we will convey it to sir. That is also an option.
Is chat feature available to the participants in
Right
Google
now, I
Meet?
am not able. Yes, right now
Yes,
I
sir.
am
I
not able
think
to see.
majority of them, they are already in Google Meet. So
Correct.
they can, right? There are almost 24 participants who are online today.
Correct. Yes.
Yeah.
Okay. I do need like a 5-minute, maybe a break. I need to refill water. I finished
So
a
we
bottle
can,
and a glass of water.
no problem.
Can we take a quick, maybe 10-minute break?
Sure, sure. No worries.
Okay. Thank you. I guess we'll start in a couple of minutes as I think few people are still not joined.
So they will be joining. I will just
So
call
should
them.
we?
They will be joining in 2-3 minutes.
Okay, so let's start then. In that case, yep, people are joining. So basically, we have covered today how to calculate module A. We have looked at infrastructure assets. We have looked at scope 1, scope 2, scope 3 emissions. And we've just looked at another standard called ICMS. So to close on ICMS, let me just share with you some couple of things. So let me first share the ICMS document itself, which for some reason, okay. So I'm sharing on my screen. Hopefully you can see it now. This is the ICMS document. What I want to highlight here for you is the very detailed hierarchy of various projects. So basically, this is what I was telling you in terms of project attributes and values. Every project, because the goal is using ICMS, carbon emissions and life cycle costs information can go sit in a database. It can be your own company's database. Let's say you've done hundreds of projects, and if you all have the same structure in which cost and carbon is stored with this kind of project information, so it gives things like location. It gives things like base date, price basis. It has piece of information such as construction period, and then site conditions, seismic conditions. All of that information is there. This is extremely extensive, actually. So life cycle cost related project attributes are there. Carbon emissions related attributes are there. So for example, did you use 15978 to do your boundary for carbon reporting and so on? So those are for all types of projects, but then for each type of project, in this case building, we have more project attributes. Obviously, these are not all mandatory. You can provide as much information. So for the very least, you should say whether the projects that you're storing in the database are all residential, maybe office. So this selection would be useful. And then if it's a hotel, what grade, and all that information. So that's for buildings. So similarly for roads and highways, we give what kind of road or highway it is, freeway, expressway, road, lane, so on. So lots of project attributes again available to you. If you store some of these details in your database, then you will be able to utilize this benchmarking scheme to create benchmarks for carbon and cost for your projects for early cost and carbon advice. So similarly, you can see for railways, there is more information. So all 18 or 19 project types have a common set of attributes and values, and then specific to that entity or project type, there are more attributes. If we adopt this kind of a system globally, then comparison becomes much easier for us. And then if I can jump to this, I hope you can see this. How are organizations using ICMS? So one great example that I always try to use is this RIBA Sustainable Outcomes Guide, the Royal Institute of British Architects Guide. In this, you will see that for basically doing life cycle costs, they have adopted the ICMS scheme. So if all associations through their members adopt this kind of a framework, which is ICMS, then you will see that we can build more and more benchmarks for our cost and carbon. So this is an excellent example of adoption of ICMS also. I'm going to stop sharing. Okay. Let me bring up another example before we close the session. So let's look at another example that would be helpful for you to figure out how we are going to move forward and do more emission calculations. So let me now share with you back on that slides that we finished off ICMS with. So this, I'm not going to go into slideshow mode. So we have another project in which we have drywall or plasterboard sheet, which is for this project, we need 400 square meters. A typical plasterboard sheet is 2.4 by 1.2 meters. So we have 2.88 square meters. We basically then need 140 boards for our project. The distance for our project and the supplier is 80 kilometers one way. So our goal is to estimate A4 emissions for our project for this particular material. So what do? We need to now go and search for carbon factors. So I'm going to take this example of UK. Okay, so I'm going to first stop sharing this and then share with you another screen. Okay. Why it's not showing up? Okay. So now you will see on my screen the source that you have to search for in order to get emissions data. In this case, we had to go to the UK greenhouse gas emissions published by the Department of, it's called DESNES, Department of Energy Security and Net Zero. So they publish. Becoming a bit challenging with so many screens open. Okay, so you will see now we are looking for fuels, bioenergy, refrigerant, passenger. Think we're getting there. Wow. Basically, what I'm trying to search for is a sheet which basically gives us, so the UK government publishes what's called the carbon factors for their economy. Okay, so if you are trying to find out user carbon emissions for your project, you can come here and it basically tells you for a small car or a luxury car, how much emissions, kilograms of carbon dioxide equivalent are emitted per, if it's diesel, if it's petrol, per kilometer that is driven. Okay. Similarly, you will see there is also a sheet, which for some reason I'm not able to find, which essentially gives you carbon emissions for trucks, loaded trucks, half-laden trucks, empty trucks. So if you look at our, I think you get a good flavor of this. I'm going to again stop sharing. Go to our Windows. For some reason, here we are. Okay. So from that UK carbon factor database, you will see for delivery trucks, this is the screenshot. I couldn't locate the worksheet, but it's there. So for trucks or delivery vehicles, it tells you what kind of tonnage you have. Based on that tonnage, you can pick up the total kilograms carbon dioxide equivalent per unit. 0% laden, which means empty return, or 100% laden, depending on whether it's full. You also have 50% laden. So using the carbon factors published here, because we don't have an EPD, for example, that gives us A4, then in that case, you have to search for these kinds of factors. So we're going to assume that we need a 17.5 ton or a 17-ton rigid truck to transport these 140 plasterboard sheets or plywood sheets. For every mile driven, you have 0.79097 kilograms of carbon dioxide equivalent that is released or emitted for every mile that's driven. So we basically have, for empty load, it's 0.7907. For 100% laden, it is 0.99337. So we basically multiply that with our distance, which is 80 kilometers. You get basically 142.7 kilograms carbon dioxide equivalent emitted for A4 for 400 square meters of plasterboard or drywall, that kind of material. So you'll have to do these kinds of first principle calculations wherever the information is missing. How do you get this information? If you are in UK, luckily the government publishes lots of this information and you can use that. But in other places, it's always a search for database or pieces of information that can help you. So you can then, maybe for future use, you can simply do an estimate and say, for moving plasterboard, bringing it to the construction site from the manufacturer, supplier, vendor's site, it's about 0.4 kilograms of carbon dioxide equivalent per square meter of plasterboard that you need for your project. So that's another example of how A4 can be calculated. Okay. So let me stop sharing. Go back to that. The next thing I want to do is show you another example of okay. I have multiple screens, so give me a minute. Okay, start sharing. Now, I showed you from a database, you can pick up, actually calculate how many trucks do you need, what's the distance you're going to travel, what's the emission per mile of fully laden truck, and what's the emission kilograms carbon dioxide equivalent for empty truck. We used all those calculations, but you should not use that those first principle approximations and search for that information if you have EPD like this. Okay, so luckily for plasterboard or for gypsum board or drywall, whatever you want to call it, Saint-Gobain or British Gypsum publishes an excellent EPD. Okay, this EPD also complies with all international standards. It is for a wall board that is 15 millimeters thick. It's called Gyprock. And we got to search for a few things here. You know, the manufacturer. You should see that it is not third-party verified. They are using a PCR. Once again, all that good information. You will see it's not saying it clearly here, but it's for 1 square meter of gyprock, which is 15 millimeter thick. So this particular EPD is for that kind of information. So if you now scroll through, you will now clearly see the declared unit. This is a must for all our EPDs. This one has extensive information available, which is not very common right now. So this EPD uses a 60-year service life, RSL of 60 years, and is able to give you A1, A2, A3, A4, A5, B1 through B7, C1 through C4, and D, which is amazing, not easily found. So I picked this example because of the wide range of availability. So you can see all modules listed here are declared in the CPD. And they describe the various stages. They describe the plasterboard manufacturing process, but now we are more interested in environmental indicators. For us, the total is what we are looking for, GWP. So you will see A1, A2, A3 value is given, A4 transport value is given. Surprisingly, they have done a study in their EPD which tells you per square meter to install that sheetrock, let's say, into an interior wall surface is that number that you see on the screen for A5 installation. So you don't even need to do first principles calculations for your A5 emissions. Since this gyprock, this drywall gypsum board, during use doesn't have any emissions, right? It's not that you're going to repair it, you're going to replace it in a very systematic fashion. So B1 through B7 are all zeros. Then they have calculated C1, C2, C3, C4. Since it's gyprock, there is no waste processing. You're going to demolish, deconstruct, transport, and then throw it in disposal. So you have zero. And there may be some benefit. You see a negative emission, which means you are getting a credit for reuse. Maybe it's incinerated, maybe it's crushed, maybe it's used for something. So in module D, you're getting a small amount of credit for utilizing this kind of gyprock. So that's another more detailed example. Obviously, there are many more indicators that British Gypsum provides. In addition to environmental impacts, they also provide resource use impacts by life cycle stage. They have lots of other optional indicators. So slowly you will see that they actually provide health related indicators also, which is not very common. So this is a pretty advanced EPD available in the UK. Yeah, I think this we already covered. And if you want to understand a bit more, for 1 square meter gyprock wallboard, 15 mm through their LCA calculations, this is how they are interpreting the results. So that's another example. We're going to go into more examples when we come back from our lunch break. So I'm going to stop sharing and open the screen once again for any questions or comments. Is anyone familiar with any availability of carbon factors by the Indian government?
Sir, I have a question.
Yes.
As you told, ICMS can be used as a database also. So
Correct.
database can be used in SEMA-Pro software because for my research work I'm using SEMA-Pro. So
Okay.
can I add it in the processes and then I can use the whole building LCA?
I think you're breaking up a little bit towards the end. So I think you said that SEMA-Pro can utilize databases such as ICMS. So what was the question in the end?
So for Indian scenario, can I use the database ICMS in SEMA-Pro? I can integrate them and use.
You can means we can only provide you with a database structure. You need to import data, and that's the main problem, right? In India, if there are no historical projects available that you can store in a database, then you have an empty structure. That is the problem. Whereas we know several companies globally which are using ICMS database to store their project information. So you can utilize data from those sources, which is probably proprietary and not easily accessible. So, for example, I can just to answer your question. I will share with you an online database. Okay. Let me see if I can share my screen. I guess I can share a tab. Chrome tab, right? I can share a Chrome tab. So you will see that Rambol is publicly sharing their project database. So you can, in this Power BI interface, you can select a country. Unfortunately, you can see how limited that is. You can select building types, so maybe residential, project type new build. And so they have 17 assessments available. So you can go and see the kilograms of carbon dioxide equivalent, the spread in those 17 assessments. It's not a whole lot, but you can see, and they're only publishing A1 to A3. There's no other information published. So you can go, maybe look at Sweden. Maybe look for educational. Maybe look for new builds. And come on. So there are only 6 assessments available. But that's what I mean by having a database that can help you maybe directly import information to other LCA software also. So I'm going to stop sharing, go and show you another database with a big data set. Seem to be having trouble finding it. Give me a minute here. So it's called CAD. I unfortunately don't seem to be able to find the actual database, but I found this, which may be of use. So another database that is publicly available is this ARUP's database. They have 88 assets, these many, but I think it has grown to like 1,000 projects now. This was in 2020, so now it is much bigger. Let's see if I can find it. No. Let me search during the break. I will share that link also with you. Okay. Stop sharing. Okay. Any other questions that you may have? Otherwise, we may end up closing soon. I don't want to start the next topic while you have to go for lunch. So any other questions or comments? This would be a good time to have some discussion. Professor Aligaonkar, do you have any questions or comments, or is it okay if we stop now and then maybe try and come back a little earlier?
Yes, sir.
What time is lunch?
Yeah. As of now, I couldn't see any question. Participants, do you have any query, anything to ask? We have 20 minutes to go. Seems like there are no queries here.
So should there
No
be
queries.
maybe a question or something, or that we can, an example calculation that we can give to participants? I have another larger example that I'm going to do after lunch break.
Okay.
But I think eventually we have to come up with, maybe tomorrow we should introduce a quiz or a small test, and then also another, I guess on Friday anyways, there is an exam, quiz or test.
Yeah, so with some of the questions, I think my team is ready. I'll ask them to just post it to you. And
Okay.
then you can go through that. Most of the things which are covered, they are already parallelly preparing some questions.
Okay, and I'll share today's slides also.
Perfect.
But maybe for tomorrow, we should prepare some sort of a Q&A or maybe a small quiz to
Right.
get everyone to speed. And then obviously the final one on Friday.
Okay.
Okay, so what time should we get back? You guys are going for lunch. I'll take a little break.
Yeah, so maybe like
2
yesterday,
o'clock?
we have continued 2:15, right? Dr. Mangesh?
It is
2:15
2:15.
is fine,
Technically,
sir.
can we start at 2 or should we wait till 2:15?
So we should wait up to 2:15.
Okay.
We'll start at 2:15, sir.
All right. I will see you guys then.
Yeah.
I guess I stay on this link and just turn off my mic and.
Sir, no, Bhagyashree will share a new link to you.
Okay.
So
All right.
you can just take a break and then we can meet maybe after 1.5 hour. So
Perfect.
10-15 minutes before she will just ping you that.
Okay. Then, yeah, we can. All right. Thanks.
Okay, sir.
Okay, so
We
we'll
also take some rest, sir.
Okay. Yes.
Continue, there are 2 sessions.
This one is the 2.5 hours is a little longer. Yes. But we'll be there. I'll see you guys again after lunch. Enjoy
Yes,
your
sir.
lunch break.
Yes, sir.
Bye bye.
Okay, sir. Rahul, sir.
how?
Sir,
Hello?
किसी को बोल, we have to tell someone to stop recording now because it is getting recorded even.
Yes. Yes.
मैं भाग्यश्री को कॉल कर रहा हूँ, वो उठा नहीं रही है.
नहीं वो यही है. Manoj is there. Manoj? हाँ. ये recording stop करो.
Okay, Sudhir.